So what I'm going to do is review things first, trying to help you understand what it is you need to know. And that's the whole challenge with teaching and testing. When you go through tests, this is true with tests in life too. There's a lot of things that we know, and often it's trying to figure out what is it that we actually need to know to apply to be able to use this stuff. And that's really the goal of any class, there's a lot of theoretical stuff that builds up to it to give you the background, but then what's the final end thing that you've got to know? That's what I'm trying to make clear to everybody. So anyway, I'm going to go back here to this picture, and we're just going to do a quick review, hopefully, of synchronous machines from the magnetic perspective and then go all the way up to the equivalent circuit. Then we're going to pick up on the open circuit, short circuit characteristics and tests, which is what was in lab 5, and why you'd use that, how you use it. More or less what I've got here is, here's a 2-pole rotor. Now this thing is off. One more thing. I can't get it kind of snapping into everything. So everything's off on this one. Okay. So the rotor is got a major wobbly thing going on here in the freaking air gap. I can't fix it because of this tool. Okay. Bottom line is, what I was trying to show you here is that you could have different types of number of pole numbers. So that's takeaway number 1. And we're just looking at the synchronous machine from a rotor field winding perspective. This is a 2-pole rotor, and this is a 4-pole rotor. What you've got to think about, it's similar to a magnetic circuit where you've got, a magnetic problem. You've got back iron here. This is a core. This is called the stator, and that is iron, right? It's like silicon steel or something. That's the rotor right there. And then the field winding is on the rotor. And I'm repeating myself a lot because this is important. Don't forget that. Okay, so because this is a key aspect of a synchronous machine, a rotating field. And it distinguishes it from other types of machines. So as a result, what you've got is an electromagnet. So for this 2-pole machine, you're creating a magnetic flux that's crossing an air gap. So you can kind of see it's going around the back iron. And I spent all this time on this picture, and now it's screwed up. For a 2-pole machine, they're not really very efficient machines from a standpoint of iron utilization and copper utilization. You've got to have a lot of iron on the stator to keep the flux uniform. The idea is that you're going to create a flux from the field, and I'm showing it in one position right now, and there's this flux driven by the field EMF into the stator. It comes back around, and we call this the flux would be phi sub p, or flux per pole. If it was a 4-pole machine, you would have 2 norths and 2 souths, and so you've got a flux lines going around this way and flux lines going around this way here. And it's going to go back. See, it's going to split up, right? Let me see, do I have this right? You got that, right hand rule, and it comes back out. Yeah, so the arrows are pointing in the right direction. So you can kind of see that. Now, the more poles that you have in a machine, see, notice how the stator, which should be this thing right here, that iron, there's less excess iron than you do in the two poles. So the more there's poles you have, you can get a better power dense machine. But what it does is it changes it changes some things. So I'm going to try to make that clear to you when we talk about poles, and I'm going to get to that in a minute. But the idea is that we have, and I'm watching my other screen. Can you guys see? Because there's a big leg on my machine.
The spatially distributed turns picture.
Okay, it just popped up now. So I think I'm behind you guys. I'm going to ignore my screen. I've got two computers. And the spatially distributed turns here, we talked about that in the lecture 1. And so it distributes the MMF in that as it goes essentially along, going around the rotor. You can think about going inside the air gap, and the MMF going around that has this distributed shape that we're showing right here. And so as a result, and here's the first key summary takeaway, in a very general sense, you're going to get a rotating field MMF. And we're really only concerned about the fundamental component. It's not a completely sinusoidal thing because of these little steps that we're seeing here. And because of those little steps, you could do a Fourier series and you'll get harmonic MMFs, but I'm only considering the fundamental MMF. And we end up with this expression, and the important points here are that you've got a total number of turns, but then your MMF gets driven by turns per pole. And so a way to look at this is to think about it as if you had a magnetic circuit, and I'm going to draw write an MMF that's, say, NF over 2, because there's 2 poles, times the field current. And I've got another one here, NF over 2 times IF. And why we're doing this is because we're looking at this and we're saying, I'm going to have a flux right here that's crossing the air gap across on the north side of this. And then that flux is going to come back around here to the south side, and I've got it there as well. And so to these equations that are derived, think of just splitting this thing up according to the number of poles that you have. So like if you have the 4-pole machine, you've got a flux here, a phi sub p, you've got a phi sub p here, a phi sub p here, and a phi sub p here. So you have 4, and you could almost think of it as dividing the circuit up into 4 pieces. And so this is the air gap reluctance that you're crossing. And then if we had a unsaturated core, it would just actually look like that. And you know, you could manipulate this whole thing. So there's phi p and there's phi p here. And if you simplify this circuit, it just becomes, looking at it from this perspective, NFIF 2RG. That would be, you know, simplifying it down. That's a very simplistic way of looking at it, so we don't use this approach. Instead, we use this more mathematical approach. So you got this takeaway here. Now the other thing is that this MMF is moving. It's the position is moving. So since the position is moving, there is a speed, and this would be the rotor speed right here, omega sub r. We might also call it the mechanical speed, omega sub m. Now that mechanical speed is equal to the speed of the MMF. So the MMF is rotating at the same speed as the rotor. And that is why this is called a synchronous machine. So the whole point of a synchronous machine is this important expression here. The rotor speed is equal to the synchronous speed of the flux. Now, how do the poles affect this? So if you have a two-pole machine, well, actually, I want to wait on that until we get to the stator, so I'm going to hold off on that. We're going to come back to the poles affecting this in a moment. Anyway, let's just finish up with this field. What's going to happen is we're going to have a fundamental air gap flux that is due to this field, driven by an MMF. So here's another very important equation I'm going to circle. These are the kinds of equations you're going to need to solve the homework problem, okay? So in chapter 4, and if you go into chapter 4 and you look at the sections that discuss synchronous machines, this is where all of this is brought out. In chapter 5, it talks more about the equivalent circuit that we're deriving. So if you're trying to find where in the textbook this is, it's in chapter 4 in the various sections on synchronous machine. And I think I listed which sections are which in our, my original schedule for the class. Anyways, if you assume that you've got a steady state, you're at a steady state operating condition, then the current that's flowing in the field is a DC current, IF. And so I'm looking at this better picture now of just the rotor, and it's moving. I've got there's the MMF moving. And the structure of this is that it has a stack length. There's an air gap distance, G. And there is a distance, R, from the center of the rotor that goes out. And this is the variable that you use in the calculations. That R is in the middle of the gap, and I have this little line that it's pointing to that's right in the middle of the gap. Another way to look at that is that you have a diameters. You've got what would be called an inside diameter of the stator. So, and we could call that ds. And you've got an outside diameter, outside diameter of the rotor. dr. So this word here is diameter. Okay, I wrote that really badly. So there will be a d, it's an averaged diameter, which is ds plus dr divided by 2. Take the two diameters, divide them by, add them and divide them by 2. R is equal to d divided by 2. So it's the average air gap distance, and that's what you're going to use in the magnetic calculations. So as a result of this driving MMF, what we end up with is a peak flux density. And so we actually go to the, I derived this a little bit differently in a more clear fashion in lecture 1 that was recorded. But in the book, it does it this way. So there's a peak flux density, which you would get by simply taking the MMF times mu naught and dividing it by G. And really, where does this come from? It really comes from Ampere's law. So you would say, well, I've got an H peak 1 that's equal to B, and let me, there's an H peak 1 times G, that's your L, and that's your length, right? So really Ampere's law, if you remember, was H dot dl equals the I enclosed, which should be, really becomes the MMF here, right? So so this part of the equation is this. The other side of the equation is the F, AG1. So this is just Ampere's law, and we know that B is equal to mu naught H in the air gap. So that's where the mu naught comes from. So it's just a rearrangement of Ampere's law. And so in the space above and below the north and south poles, you will get at this pole flux, or flux per pole. And looking directly at this picture here and the dimensions that are given, you get this expression here, but the final expression that we use typically is this one. So there's another equation that you need. And this flux, so now we can start talking about the other windings. So are there any questions so far on this? Adam, you got a question. Do you want to say anything?
Yeah, for your equation for B,
Yeah.
if B equals mu naught H, why does mu naught end up in the numerator in the final equation?
Yeah, let's figure this out. Did I screw something up? B is equal to mu naught H. Oh, that's because H, okay, so here H is F over G.
Yep.
Right. So this is the H right here.
Yeah, I get it.
Yeah, it's a little bit confusing, and you have to think about it carefully. Okay. So that's good. Can you take your hand down, Adam, just to make sure I don't get confused? Thanks. Okay. Now this flux is going to, again, we've got more than one winding involved, so we're introducing another winding. The flux crosses the air gap right here. And we can kind of think of the flux that we just derived as the peak flux in this region. And it is going to link up with another winding. Now remember, flux linkage, if we had a mutual flux linkage. So let's say you had winding 1 and winding 2 And you wanted to know the mutual linkage, flux linkage would be lambda, in this case I'll say lambda 2 due to the flux of 1. And I'm going to say, okay, well, this is an A phase winding. So you kind of guess that we're going to have 3 phases. So we have A phase winding. So that is, and so what is the flux linking phase A due to the field winding here? So you could rewrite this as, so if you had lambda 2, 1, it would be the turns 2 times the flux 1. And we've got then lambda, let me think here, we write it the different way. No, that's right. A is 2, F is 1, lambda AF. That's going to be N, some NA, I'm going to say effective because we have a distributed winding, times that flux per pole that we derived. So this is really what we're doing. But now you have to remember that this flux, and this is the key point I want to make clear to you all today, is moving at a speed omega r. It's not standing still. So this flux per pole is actually, we derived, this is kind of a peak. If we consider it from this viewpoint of the thing that is on the stator, and then that is a peak flux of a sinusoidally varying flux according to the movement of the rotor. And that is, you know, when you look at these electric machines, what happens on the stator is what you measure. That's what you see. And you're going to basically, what you see on phase A, that's where you can actually measure. You can't really measure exactly what's going on the moving part, but you can measure what's going on the stationary part. So what you see on the phase A is a phi as a function of omega RT. Or you could say omega ST, because omega R and omega S are the same thing. So then what we have to do first is we say, well, let's, and I'm not going to go through it, but we derived a basically a distributed MMF associated with current flowing through the one-phase winding at one point in time. It's kind of a scalar point. And then you find a turns function in the same way that we describe all of this in lecture 1. And if you don't go watch lecture 1, you're going to be lost on this stuff. So now what we end up with, and I'm going to go to the result of lecture 1, is we end up with this expression here. Okay. Which is a varying flux linkage, linking A to the field. So the end game is, what we're trying to talk about is we've got lambda AF. And I'm going to talk about this. This is where I'm going to talk about poles. Lambda AF is the turns of the stator phase, so there's a winding factor that takes into account how well you're distributed, times the turns of the phase. Make sure I'm not missing anything. Yep. And then that simply gets multiplied times a time-dependent flux. So you have a time-dependent flux linkage because of a time-dependent flux. And the time-dependent flux is, let's go back and try to understand where that time dependency comes from. So we go back up to the rotating MMF function that we showed right here. This function here. This is the time-dependent term, cosine of all of this. And so I'm going to go back down and I'm going to capture this, write this out down here. And we've got then the MMF is proportional to the flux, peak flux. So we've got a flux per pole, that's the peak, cosine of poles. Here's that speed. It's and then I'm actually putting in a kind of an arbitrary angle, which I'm going to call theta m. But it could be 0. It could be something else. And we're going to understand what that meaning is in a few minutes. Now, if I look at this, I can also write it in terms of synchronous speed. Poles omega synchronous t plus del m. Now, when you do your open circuit test on one phase, you're actually measuring the electromotive force associated with this flux linkage. So EAF is the derivative of lambda AF dt. And so you're going to have something that's going to be a sinusoidal function, and there's going to be a frequency of that function that's electrical. So we're going to say I have an electrical frequency, omega E, that is poles divided by, there's a 2 in here, divided by 2 times either the rotor speed or the synchronous speed. They're the same. So this is the key expression that you need to know here also. That relates it to how many times the flux variation occurs per rotation. So if you want to put it in terms of mechanical speed, you could write it like this. Now there's another thing that typically happens is when we get deeper into the machines and we talk about them usually as motors, not so much, I guess it's as generators too. So really when you're saying equipment perspective of things and you start looking at the nameplates, the nameplate is the information on the machine. So those of you who've been around motors and generators would know this. There's usually a nameplate that specifies the V line-to-line rating, the I line rating, the number of poles. This stuff is always available to you, usually on a nameplate. And then they're going to give you the mechanical speed. Does anybody know what they usually give the speed in what units? Anyone? Your car does it too. There's that extra little dial that we ignore when we're only looking at our, I guess maybe.
You said RPM.
That's right, RPM. That's right. Okay, so typically it's N. That's the symbol that the class uses, is defining the speed in RPM. And so there's a conversion factor between this speed here, omega r, is a speed in radians per second. So you have to do your calculations based on this. What does RPM mean? It means revolutions per minute. So if you were given RPM instead of the radians per second, you'd need to be able to convert between them. Really what it's saying is that you have 2 pi radians per 1 revolution, right? And there's 60 seconds is in 1 minute, per 1 minute. And so what the conversion factor between n and omega r ends up being 30 over pi. Okay, so here's another thing. We won't use this so much in this module, but modules 6 and 7, we're going to use it all the time. 30 over pi times omega r, or going the other direction, omega r would be pi over 30. I just know that the omega r is going to be much smaller than the RPM speed. Okay, so this ties back then if let's just say an example. If you have a 4-pole motor with 1800 RPM, what is the electrical frequency? Well, actually, and what we really want to know is Fe, not omega e. We never use radians per second. We talk, when it's not meaningful to us when we're really talking about, the things that we specify and stuff like that. Okay, we know that omega e is 2 pi times Fe. So how do you find that? So you would basically say, I know that omega e is equal to the number of poles divided by 2, or pole pairs, times the rotational speed. So I could say that's 4 over 2, and then I could take pi over 30 times 1800. This is going to give you 377 radians per second. And so that Fe is 60 hertz. So 1800, and we use 60 in the US. Other countries use 50 hertz. So people in the US they know if I got an 1800, I've got an 1800 RPM machine. I know right away that's a 4-pole machine. I know 3600 RPM. Right away I know that's a 2-pole machine, and so on. So, you get used to these numbers. But anyway, so that's a little example of how poles are affecting everything. Is there any question on that? I want to make one other slight point. Talking just about the rotor now. Is we have this position-dependent flux linkage right here. Okay, so this is the important expression here upon which everything can be derived. You can move from here back and forth using all the other equations I've given you to equate electrically what's happening magnetically. And that flux linkage, though, right now, the way we've described it, this was done for a round rotor. Well, it actually doesn't matter here at this level. But if I go back up to this level here, I have an MMF that is changing with speed. But my air gap here, distance, doesn't change. That does not have any variation with position. So essentially, with this round rotor machine, the F has the position dependency, and I talked about this before. Remember that flux gets converted from F using the reluctance. So if you take F and you divide it by the reluctance. With rotating machines, it's more convenient to talk about permeance. So you have F times a permeance function. And so we're really going to start talking more about the flux this way. And so I have a constant permeance because the reluctance doesn't change. You know, you remember reluctance is L over mu A area. So permeance would be mu area over L. Okay, so that's a round rotor machine. The thing that's giving me the position dependency that's actually enabling me to create a voltage is the MMF. Now if I had, there are different types of machines that we introduced in the beginning. So here's a salient pole machine. In this case, obviously your MMF still is varying with theta R. So you still have a F that varies with theta R because the MMF provided by this field is moving. But you also have a permeance with a theta R dependency because the air gap, that's this area here, is not constant with position. And so it's a more complicated structure when you start analyzing it. We don't focus on this, but just to make you aware of that. And then I wanted to show you this picture of it's from the textbook, but this is for a 4-pole salient machine, which was similar to this 2-pole. It's just like this, if you remember we drew it. You got this kind of structure here. That's these things right here that I'm talking about. There's your rotor. So this is a cutaway, and you're going to put current into the field windings that are wrapped around these. And how you get that in there is through slip rings, which would be, there's brushes and slip rings. It's maybe a little bit difficult to see, but they're in this region right here of the rotor. So you're bringing the current from the outside, just from another supply. It's a DC current, and it's going to come through like, I don't know if it's these two things, but there's two slip rings that are in contact with brushes. So the IF is coming in there, and it's going out there from some supply. That's your field current. So you have a rotating MMF. Any question about that? Okay, so let's go back and look at the stator for a moment. So far we've only described one phase, which is right there. So that's your phase A. But in its the phase A is occupying these slots. So you have empty slots. It follows that you could distribute and put other windings in these slots. And what's interesting about this is, notice that this is the A here. And so you can think about it this way. The current is coming out, so this is a generator. This is the A connection of the generator. You've got current IA flowing out of that generator there. Let's find the B. Now here's the other end of it. This is the A. Now where's this going to connect? Where would this connect typically? Can anybody? You guys got to be able to tell me. Somebody does. From the last lecture. Not ground.
Negative.
Not ground. But it's close. What is it? It's a reference, right? Neutral. So we have this common point that we call neutral, right? So we essentially have one phase of this thing, right? So far, I've got IA coming out of here. And there's a lambda AF associated with that coil right here. And we could, in the time domain, it's really kind of going to be represented like this. We did this last time. We have an EAF, and everything simplifies down to a synchronous inductance dIA/dt. Everything I'm showing you is in periodic scalar right now. We went to phasors before, right? This is the neutral connection right here. So that's everything I just talked about here. Now, if you look physically, what we have, we're going to go over and let's find there's an A and there's a minus A first. So this is A, this is minus A connects to neutral. So let's find the B. The B is right here. And the minus B is here. So I've got this group of slots that would carry the turns for phase B, and we could draw the structure like this or this, and there's your B, and there's your minus B, right? So the minus B right here, I'm going to make it say it's a different color. It's this green, or not that green, this green. So essentially what I've got X's coming out here. I'm going to connect all the X's together, and dots here, because it's generator and the current is coming out here. There's the B right there. And now if I follow around, I'm going to find a C, which I believe I need to use a blue color because I'm trying to line this up with something I'm going to show you. Okay, so here's the C. So the dots are here and the X's are here. So physically arranging these guys in this way there is a very important reason for doing this. And then this point here comes back and connects around to the neutral. So I've got the other, there's the C. So I've got that, and I've got this. Okay, does that make sense to everybody so far? Are you with me so far?
Yeah.
Now the trick is this. You have a distribution around, if you think about the fact that there's a flux that's moving around this direction, you know, you can think of it as flux in the air gap is moving into this position, theta A. And there's a position dependency of the individual MMFs of each phase with respect to the rotating field. And what does this do? And this is what I'm going to show you what happens. And there's several animations on our this link. I was mistaken. I didn't put it up. I thought I did. It's now on the it's now up on Canvas. I think this is the one that I like the best, I think. Yeah, okay. So here's what's actually happening because of this. You have these spatially distributed phase windings, and each one of them has an alternating current going through it. So the phase A is the red one here. Because the current is time dependent with omega E, so omega ET, it's going to be going from a spatial perspective, and I'm looking on the x-axis here at the angular position in the rotor, in the air gap. The sine itself is just changing in amplitude, but it's staying fixed. The same thing with the blue, but there's a 120-degree phase shift on how the AC current goes in, and there's also a mechanical 120-degree phase shift, and then with the C as well. So you have ABC. Now what we're doing here really is we're going to say, okay, there's a total MMF, and this is the main point I want to make. There's a total MMF associated with FA, FB, and FC. So I really have what each of these are is I have a n terms function of the A winding that has some position dependency times a current that has a time dependency omega ET. So I'm really putting in a sinusoidal current of IA. T, for example, is I, some I peak value, cosine omega ET, and then there's going to be some power factor angle in that current. The IB of T is I peak cosine omega E T plus phi PF minus 2 pi thirds, or minus 120, and the IC of T, I peak, so in degrees, 2 pi thirds is 120. Cosine, we did this, you know, in module 1, we looked at the same thing. We looked at, remember, the scalars that we were looking at? So these three currents, this is IA, this, now the other thing that's happening though is, and one way to really simplistically look at it is, what's this theta? Well, that theta ends up for a synchronous machine being poles times the synchronous frequency divided by 2 times t. And we know, what is this? Anybody know? Well, what frequency? What do we call that frequency?
Wasn't that omega s?
No, it's omega E. Electrical frequency, right? So we kind of have a physical speed and we have an electrical angular speed. And then we get a frequency from that, right? Okay, so this is omega E as well. So really you've got these cosine terms that are multiplying together, and the total MMF adds up together. So you can do this mathematically, and that little handout that I have comes at this problem 3 different ways. One of my students years back put that together. He got so into this stuff. So it's not like this is nonsense, you know. Real life students have been able to figure this stuff out. Except OneNote is nonsense because it's doing stupid stuff right now. Okay, so essentially the total MMF is the sum of these MMFs in the air gap. So they all add up together. Now what is the effect of that? That's shown in this animation. If you were to sum instantaneously at any point in time, it's that black sine wave. So what you have is a sine wave that's moving with position. That's exactly what we have the rotor doing as well. Remember the rotor, I said it's moving, and we were describing its movement, the fundamental component of its moving MMF, as a sine wave, right? So I really have 2 sine waves. So what we're really saying is that this, now we tend to call this FA, but A doesn't mean A phase, it means armature. So what we've got is we have an armature MMF. So we have really effectively 2 windings. We have a field winding with an MMF, and we have an armature winding with an MMF. So it's quite simple. What you can think of it more simplistically that way, and it ties back to when I introduced this and the Lorentz force law and everything else. That's what this handout does that I shared with you. But essentially, you're going to have, as a result, a armature MMF and a field MMF, and they're going to be displaced by an angle del M, and this was the torque angle. And if we do pole pairs over 2 times del M, we get something called del or del E. So that torque angle, or this is really what I would call the power angle, because we're now looking at it in terms of the electrical system. If we look at it in terms of mechanical things, we would call it a torque angle. And remember that the torque was proportional to negative sine of this del. I could say del mechanical in this case. So this ties back to the Lorentz force law stuff that we learned. So what you have there, this is just the MMF from the stator, from the armature. The black is moving at a constant amplitude as the rotor turns. And let's see if I can find one that shows the field as well. I'm not sure if this is actually showing the same thing a different way. So the phase A, when the dots get bigger, that means the current's at a higher level. And then notice that it flips from a dot to an X. That means the current reverse direction. And this just shows, again, the same thing a different way. Okay, here's the, none of these pictures are doing exactly what I want. This is the other MMF moving, and it's showing kind of the motion of the armature MMFs together. But what the bottom line is what this is doing is this. I have to draw the picture myself now. I'm going to clean this up. You've got a rotating structure, and we have a field MMF. Which I'm going to draw as this green arrow, right? And it's moving at the rotor speed, or synchronous speed. Maybe it's better to say synchronous speed. You've got a rotor shaft to draw the complete parallel here. In the middle, right? There's a shaft coming off of this, moving, and you can kind of think of it that's the oh, hold on. It's moving at the mechanical speed on the shaft. So I think of omega r is the shaft, omega s is the flux. So there is an MMF that is moving also at the same speed, and I can describe it as another arrow from the armature. And so this would be the MMF from the A, or the F armature. So the A doesn't mean A phase, it means armature now. And the MMF from the field is this right here. And they're both moving at the same speed, omega s. And there's a fixed displacement between them, and that would be del m. So del m is the torque angle. And if you can think about it, if del m was 0, there is no torque. Sine of 0 is 0, right? If del m equals 90 degrees, that was what we were talking about, max torque per ampere. Now with a synchronous machine, you can't achieve this because of the synchronous reactance. Which we talked about last time, right? And so essentially, I'm describing here everything that's happening in the mechanical world. Now here's your electrical equivalent circuit down here. And what I just described here, because the del M was negative, was a motor. So that would have meant that the torque would be in this direction going out. Essentially, you're putting torque out. And that would correspond to, I copied both pictures here. So here's your motor. So we also have an equivalent circuit for this. And then this is your generator here. If I had a generator, this blue line right here would be over here on the other side. You know, you'd have a, if you can imagine, the armature that direction. Any questions about that? Does that make sense?
Yeah.
Yeah. Okay, so now we can connect. We really have got everything connected up. Now I'm going to use a, give me a few more minutes. All these technical things have screwed up my... Take a couple minutes and let's talk about a generator for a moment here. And we're going to have to next time give the examples. But remember in the lab, you had to do this by video, unfortunately, but you were operating a synchronous machine as a generator. If you're at no load, if there's no load on the generator, then IA is 0. In this case, we're looking at IA. I want to make sure everybody's clear. We're using A in two ways. A is A phase here because it's a single phase equivalent. We know that if we just do one phase, we can get the answers to our problems and multiply things by 3 and square root of 3 and so on. But also, when we talk about the A up here, we're talking about armature. But there's really a symmetry here, because you can think of this synchronous machine just being described in terms of an armature to field EMF also, and an armature current. So the A is a good subscript to use because it just physically tells you kind of what's going on. And but if IA equals 0, then the voltage VA that you're measuring is equal to EAF. So another important equation that we've learned was that the magnitude of EAF, which you could say is EAF RMS, is square root of 2 pi FE kW phase turns times the flux per pole. You could actually then go back through all the equations that we gave you earlier. This is a function of the field current. And so in the lab, we're able to create a open circuit characteristic by operating at a constant speed. So you say at omega r constant, and change the field current values and increase the voltage that you're getting. And the open circuit voltage actually tends to follow a curve. It looks a lot like a BH curve, doesn't it? So the EAF really defines and is proportional to the flux density. And we would know that by going back and looking at all the equations that we showed up here up before. Phi P is proportional to B peak. And so you can tie this even back to the iron if you want. But what the lab that we did shows us a method, and we're going to have to finish this at the beginning of the next period, of being able to derive this here, the synchronous reactance, by performing first an open circuit test, and then secondly performing a short circuit test. And so if you did a short circuit test, you would take this same circuit here and you would short the output and do the same thing, vary the field current to vary EAF. Now the VA is equal to 0, these two tests together enable you to come up with this expression for XS. And that's the purpose for those two tests. What comes out of the tests, as you saw in the lab, is a short circuit ratio, short circuit current ratio. So a little teaser, of course, this was covered in the lab, but there's a short circuit current ratio, and it's typically given with any data sheet for a generator, is equal to 1 over the per unit value of synchronous reactance. And so you find the short circuit current ratio, which I'll explain that in the next lecture. And that gives you an inverse of the per unit synchronous reactance. And then if you know the rating of the generator, you can go ahead and find the ohmic value of X sub S.